All right, so let's reconvene our conversation about air pollution. We just started. So we've kind of wrapped everything up with water pollution. As we move into air pollution, we've had small conversations so far, very small. But you all have a huge wealth of knowledge about air pollution already, probably a majority of it coming from popular media, popular images, popular news clips, things about air pollution. On your paper, please write down greenhouse effect in terms of today's topic. We're going to talk a little bit, we're going to go into lab, and then we're going to come back and talk. Just like 5Es are the backbone of how we lesson plan for a lot of our things in science. It's the lesson plan model of inquiry. So 5E says that a child is going to learn science by doing science. So the lesson plan of 5E, engage, explore, explain, elaborate, evaluate, those 5 things are the same 5 things that scientists do. There's a testable question. That's engage. So I open up with a question. All science starts with a question. All 5E lesson plans start with a question. As soon as a scientist has a question, they collect data. That's explore. So the scientific methods mirror the 5Es. 5Es are the scientific methods so that the students are learning science content by doing science. Now, not everything can be taught that way. If I want to teach a kid how to use a microscope, I'm not going to do a 5E lesson. I'm going to show you how to use a microscope. There's no data to collect. But if there's a testable question that you can collect data with, that's the 5E. And I always tell people, if you're a little nervous about the 5E, there's a simple thing to do. Take the experience and put it before the explanation. Then you've already established the backbone of the 5E. You've already said, here's a question that we're going to go figure out. We're going to collect some data, and we're going to use that data to build the explanation, just like a scientist would. Scientist has a question, collects data, makes an explanation. In a 5E inquiry lab, we start with a question, we go into data, we go into lab and grab some data, we come back and make an explanation. So 5E planning mirrors what real scientists do in the real world. The answers, I'm looking at what information is already rattling around in your head. Lauren, go.
High levels of CO2 in the atmosphere.
Say that one more time.
High levels of CO2 in the atmosphere.
High levels of CO2 in the atmosphere. When you say high, what do you mean by high?
I mean that there's already carbon dioxide naturally occurs in the atmosphere, but by burning forests and coal, we increase it.
We've got natural causes. What do we call the word for human related or human cause?
Cultural.
Cultural in terms of eutrophication. What's a big long word starts with A?
Artificial.
Ooh, anthropogenic. Anthropogenic, meaning human related. So, this class in particular, I have 10 or 12 incredibly strong, vocal, confident people. They're always going to dominate. So I have to assess the others in a little different way. So that prior knowledge probably gets pulled out in different ways through different people. A lot of it was informal conversations back in the back. One of the students in particular I know is never going to speak up in that situation, but she'll speak up when I go chit-chat with her in the back. So I don't get everyone's prior knowledge all at once, and I also don't get it all verbally. So we've got natural and anthro causes. Okay, so carbon dioxide, huge, huge, huge piece of the puzzle. Is that the only piece of the puzzle we have rolling around in our heads?
No.
What else do we know? What else do we know? Anybody? Yeah.
It also includes water vapor, and methane as like some of the greenhouse gases.
Water vapor, methane, carbon dioxide. So Lauren kind of alluded to where, yeah, CH4. Lauren kind of alluded where carbon dioxide is coming from. What about water vapor, Neil?
Well,
or go ahead, whatever you want to say.
In reference to methane, we learned in our agriculture unit that the methane is coming from anthro, I guess the human one, where we put all the cows in the field, that process.
Cows, absolutely. Waste gas from cows, absolutely. Waste gas from a lot of organisms. Yeah.
Also, like methane can also come from landfills because, like, when you like starve of the organic compounds of like oxygen, it essentially like leads to formation of other carbon compounds such as the one I just mentioned, methane.
Okay.
And
okay, so we've got conversations about carbon dioxide rattling around our head. Adam, what are you going to say? All of this is so critically tied to all of those conversations we had very early on in the year about biogeochemical cycles. Carbon cycle, sulfur cycle, nitrogen, phosphorus, water, all of those natural cycles existed long before we were here. Because we are now accelerating it and changing it and pushing it around, we're causing problems. No one's mentioned water vapor yet. What do we know about it?
Makes clouds. Oceans.
Okay, clouds, oceans. You're saying wet words at me. All right, Neil.
Increased rainfall.
Okay, yes, rainfall has water vapor in it. Mr. Hansberry.
Kind of like when pollutants are in the water, it can be evaporated, and then those chemicals can combine with other pollutants in the air.
Let's keep that word in mind.
Higher temperature.
So higher temperature causes more what?
Evaporation.
And if more evaporation leads to what in the atmosphere?
more water vapor.
Okay, so higher temperature, more evaporation, more water vapor in the air. What does that then do?
More heat.
Traps more heat, therefore we have more what?
Higher temperature.
More evaporation. And so what do we call that thing? You guys have jumped ahead to the end of the lesson. This is phenomenal. Dominoes, okay, good. What's
Getaway
that?
effect?
It's just like
It's part of the hydrolytic cycle. But let's think about this. So here's a body of water. If I put heat on this body of water, I cause, well, evaporation first. And so I'm increasing the percentage or concentration of water vapor in the air. Zorana's already said that the more water vapor you have in the air, the higher the temperature. So the higher the temperature, you're causing more evaporation. That is a positive feedback cycle. Write that phrase down. Let me ask you this question. How do we know this? How do we know this? Where does all this information come from?
studies.
Studies. What kind of studies?
Weather studies.
Weather studies. So we're looking at weather. What else? Yeah.
Controlled experimentation.
Controlled experimentation. Everything has to be controlled experimentation. As we do controlled experimentation, this is what we're going to look at today. We're going to look at what relative impacts those three things have on global warming. Unfortunately, we are not going to work with methane. Too dangerous in here. We are going to work with
Surprisingly.
water vapor and CO2. Why do I put the CO2 in brackets? What does that mean? Concentration. Good. So we're going to look at the concentration of carbon dioxide and the concentration of water vapor. Write the testable question down, please. If I'm going to teach through inquiry, we have to start with the question, what's the relative impact of these greenhouse gases? Then we've got to go into the lab and make lots of mistakes and be messy and collect data over a couple days, and eventually we'll answer that question. That question means more to them than SC 1.2.1.4. That's relative, that's purposeful, it directs them. And it's also inductive rather than deductive. If I'd put up there, we will learn the following about the greenhouse gases. I've already answered the question. What's the point in coming back here and doing it? If you had to take a gut guess, which one of those two gases do you think has the greatest effect on temperature change in the atmosphere? Neil?
CO2.
Why?
Because the larger the amount of CO2 in the atmosphere, the more it traps the rays from the sun.
Okay, so the more of this, the more heat we trap. Okay, so we've got kind of a vote for here based on what you already know. Say that again?
We use a lot of CO2 and we release it a lot more than it's supposed to be naturally released.
So we use this a lot. In what form typically? Fossil fuels. Okay. Via.
I will go with the water vapor primarily because there's more of it in the atmosphere than there is CO2.
Yeah.
Say that, who said that over here?
I said also it's a positive feedback cycle.
Is this positive feedback cycle? Can anyone think of a situation where more carbon dioxide in the atmosphere would drive even more to come up? Go ahead. Was that a, I have an idea and I don't.
Well, I was thinking about it, but then something else came into play. Like, that's when the human use would be a problem. Cutting down trees and forests increases the amount of CO2 in the atmosphere.
Why?
Because you don't have enough plants to process the CO2 through photosynthesis.
So, carbon dioxide in the air, tree takes in carbon dioxide through photosynthesis. So deforestation decreases or increases CO2 in the atmosphere? Increases. Anybody still want to have some more votes? Which one do we think is more important or more powerful, water or carbon dioxide?
I like what Neil was saying with the CO2. When you have more CO2, it traps more heat into the atmosphere, which means that the atmosphere is being warmer, which increases the evaporation of water.
Okay, so you're kind of saying that this drives this even more.
And that's why it's more powerful.
Does an increase in this drive itself more? Because we've already said if there's a lot of water vapor in the air, it increases the temperature and drives itself to be even more. Does this one drive itself?
What do you think?
Unless we do the job, it doesn't.
Say that out loud.
Unless
Go.
we do the job, it won't drive itself upwards. CO2.
So take us out of the equation.
Then that it will not. Eventually, it will go down.
It naturally balances itself. Hopefully.
If we take ourselves, then the plants will.
Say that again, Viet.
If we take ourselves out of the equation, the plants will have time. Theoretically, should have time to, like, get back up in like amount, and then it should like take the CO2 out of the atmosphere, at least theoretically.
Keep in mind the human population factor in all of this. Every single one of these issues we've talked about all year long is directly related to human population. That exponential growth curve of population is influencing every single thing we talk about. Every single thing. We can't forget that our human involvement changes everything here. In the lab today, we're going to be generating some gases. The easiest way to make carbon dioxide is obviously the old baking soda vinegar trick. I'm not going to give you a lot of instructions for the lab today. I'm really just going to say go do it. But I do want to bring out some little specific safety points. Matches. When you strike a match, be incredibly careful with who lights it and where you light it and who's around you. You're going to make a little jar of water so that you can put your match in as soon as you're done. Girls with long hair, please be sure it's tied back. We're all going to be wearing goggles. Let's just practice basic safety procedures here. But be very careful with the matches. Be very aware of your surroundings. Baking soda and vinegar. When we make carbon dioxide, how could I get the carbon dioxide from this reaction into a little test tube? We're going to be using lots of test tubes today. Okay, I could make a balloon. How would I get the carbon dioxide into the balloon, though? Oh, okay, so kind of stick it over the top and let it inflate. Okay, that's one way. I don't have any balloons. What's another way? That's a nice idea. I didn't think of that. So how can I get carbon dioxide in a test tube? If this is a test tube here, and I put the baking soda and the vinegar over here, how can I get it in here?
Hold it over.
Hold it over the top?
No, it'll rise up.
What's one property of carbon dioxide that's very helpful here?
It sinks.
Opposite. It goes down. All you have to do is pour it. Take your test tube, put a little funnel in the top, make your carbon dioxide in a little cup, and pour the gas. You're going to have liquid in your container. Pour the gas into the beaker. Now, don't pour the water in there. But when you make your carbon dioxide, when you put your baking soda and vinegar, you're going to have all that fuzzy stuff and liquid. The gas is going to be floating in the cup, or not floating, but sitting in the cup. Just pour the cup over, and it's going to fall right out. So you won't see anything pouring in there. Just keep pouring until it's going to look like a crazy person because you're going to pour just a little empty cup into a test tube. So that's how you're going to get the baking soda in there. Viet.
How exactly are we going to make sure that the CO2 stays in the cup? Wouldn't like if some of it eventually like get out?
No, and you're going to do it rather quickly. And as long as there's no big movements of your hand to knock it out and get air currents, it'll sit there because it's so dense. Okay. It'll just sit right there. Yeah. Your exhalation. You're going to look at the carbon dioxide from your exhalation. You're going to breathe into the test tube. So that's another way to get carbon dioxide. So you're going to breathe in it. You're going to pour carbon dioxide into it. And you're going to light a match. When you light a match, the easiest way to do it is to flip the test tube upside down, light the match, and just hold the match underneath the test tube. The heat from the ignition and the combustion of the match will drive the gases up into the test tube, and then just cap it off. To get the water vapor, take your test tube, fill it with water, pour the water out, and you're going to get a nice coating of water droplets all on the sides. That's all that is. No atmosphere and atmosphere alone. When you do your probes, your temperature probes, not putting a test tube on it is going to count as no atmosphere. An empty test tube on the end of it is going to count as just our natural atmosphere without anything introduced inside of it. So you're going to be running temperature with the probe and a test tube taped over it. So we'll have an empty test tube, a test tube with the matches fumes, a test tube with the carbon dioxide, a test tube with the exhalation, and a test tube with water vapor. So you're just going to try different things at the end of the test tube. Make sense? And then one person from each group come and get a lab quest, please. Yeah, it's fine. I do it all the time. All right, put the goggles on your face, please. Put your goggles on your face, please.
Exhalation, ATM and wet tube, no ATM.
Yeah, go over your glasses if you've got glasses. If you just pull it. All right.
ATM and water.
Will one person from each group come and get a vernier probe, or two, however many you want? We've got 12 of them, so you can get up to 2 each, please. I try to cherry pick what we do hands-on with to be the most important content. I want them to see data that supports the big ideas. Greenhouse gases, that's a huge thing. We could have come back here and did a lab on acid rain, or we could have done a lab on basic air pollution, particulate pollution. Those are small things. So I have to be very careful about what I have them do hands-on. Greenhouse gases is huge. So I pick what I want them to do hands-on with, and then I have to let them have the experience. The last thing I want to do is give them a recipe to follow. I need them to go and make mistakes and collect data and wrestle with data and find things that are wrong. And it takes longer to do it that way. It'd be much quicker if I just, here's your recipe, follow the following 10 things. Don't ask me any changes. Don't try your own ideas. Just follow this through and be done with this. We can get on. Be a lot quicker, but it's not real science. If you will gather around it so that everybody in your group can see the screen, that's really important. So we can all see the screen. First thing I want you to do is take out one of the temperature probes and plug it into channel 1 in the back. You'll see the white part of the plug. Put it into channel 1 in the back. Turn it on, and you should start seeing a temperature reading immediately. Is there anybody not seeing a temperature reading? Is there any validity in Skylar's group wanting to know the data that Andy's group got? Would their group want to eventually know their group's data? Why? Right. More tests, the better. Absolutely. Science is empirical. We have to have empirical data. So that means that everybody in here has to be doing the same thing. There needs to be a lot of group-to-group conversations. The only thing that I'm going to ask is when you set up your heat lamps and your temperature probes, the one thing that I'm going to ask to keep constant is 6 inches away from the light. So however you use your ring stands or your clamps, I want you to keep it 6 inches away from the light. Now you could line up 4 or 5 kind of around this. As long as they're all 6 inches, we should be okay. Here are the test tubes. So you're just going to put a little piece of tape down there. Don't put a big piece of tape right here because you're blocking heat at that point. Put just a little piece of tape around the side down here, around the bottom. You've got your test tubes, you've got your caps, you've got your matches, you've got your beakers for water. We've got 4 heat lamps. These heat lamps are probably going to live in these 4 lab stations. That means you guys need to share lamps with these 4. Vinegar, baking soda to make your carbon dioxide. Use 25 mils of this and a scoop of this. There's plenty of jars and beakers. You know where everything is. We're going to have bigger, more in-depth conversations after we have data. Get data first, and let's come back and talk about it. Okay? Does anybody have any questions before we move? Let's do another one. Let's slide another one. And then just blow it out and keep it right underneath it. There we go. Nice. All right. Now, what problem are we going to have if we immediately test that right now? What's different between this test tube and everybody else's test tube right now? It's hot. So we got to wait to let this cool down for a second, get to room temperature so that everybody starts equally. Yeah, good. Because that's adding another variable that we definitely don't want. A minute or so, it should be fine. And while you're doing that, you could set up, so you've already got your time to 310? Yes. All right, good. Now, where are you going to do your heat lamp? Which station are you going to use? Because you got to heat it up. So you got to put it right in front. You're going to need it 6 inches from the heat lamp source. So you could either clamp to them and share a lamp with them. You can clamp with them. It's completely up to you, wherever you want to set it up. Are you going to blow it out? There you go. There you go. All right, cap it up. Perfect. That's what we want. Nice job. Drop that in the water.
So let's sit for 2 minutes, you said?
A minute or so should be fine.
Nice, look, you can see it.
Yeah. That's really cool.
It's like confusing.
And then just pour the vinegar right into there, and then you're going to get the fuzzy buzz.
Should we wait until we're about to test it?
Yeah, right before you
That was really cool.
That's the way to do it.
Well done.
We had a question. We collected data. Let's answer the question. We're going to see, well, I won't say what we're going to see because I'm not sure myself. So let's see what we see. Who started with no atmosphere? Who's my group with no atmosphere? Kaylee, what did you guys get for your maximum temperature?
Our maximum was 33.1.
Okay.
And our minimum was 27.4.
Okay.
And our mean was 30.6. Did somebody calculate the change yet? 5.7.
Everybody, please write that data down because you'll need everybody's data somewhere. All right. Who had my plain atmosphere? Who had that one? Go ahead, Jordan. Read it to me.
Maximum is 29.7.
29.7.
Yeah. Minimum is 27.5. Change is 2.2.
2.2. Okay.
Yeah. And then mean is 28.8.
Atmosphere with the match. Who did that for the first time?
Yeah.
Who was group 3? 1, 2, 3. Miranda's group.
Yeah.
What did you get?
Who, me?
Miranda, yeah.
29.2.
29.2 for maximum.
Mm-hmm.
Minimum.
26.8.
Change.
Who did change?
2.4.
And 28.6.
28.6. All right. Who did vinegar and baking soda? Kevin. Let's rename you Patrick.
Okay, our max is 39.4. Our minimum was 29.1. Change was 10.3. And our mean was 34.7.
Okay. ATM plus exhalation. Savannah?
Our maximum was 35.6. Our minimum was 27.1. Our temperature change was 8.5. And our mean was 32.
Water vapor? Who did water vapor? Andy.
I have a question.
Yeah.
The ones that we did, do we keep our data there, or do we use the class data?
Let's talk about that. Do you keep your own data or do you use the class's data? Which one do you think? But you don't disregard your data. Your data is part of this. Don't disregard your data. So who did water vapor? Anybody do water vapor? Yeah. All right, Savannah,
It was our
go.
group.
Miranda. Well, go ahead.
Oh, the max was 34.5.
34.5.
The minimum was 25.2. The change was 9.3. And the mean was 30.4.
Cool.
Make sense?
Yeah.
Any surprises in that data?
Yeah.
What?
Some in ours, it was colder than the rest of theirs, but that's because we think the air conditioner came on.
One of the things that we noticed over here, and Jake and I were looking at it, all of a sudden we would see the temperature plummet way down, and it just kicked on again. Because of the way the air conditioner moves in this room, it comes down and cools that over there. So Jake, which one of these was your data that you used? Which one of these? Match.
That's before it came on.
So this is before, oh, okay, so we're good here. Does anybody's data not match? Is there anybody's individual group data that doesn't match relatively this? Did anyone get any numbers that don't match this? Lauren?
We did runs 2 and 3 with ATM only in the match, and we got temperatures in the 38 and 37 region.
38 and 37?
No, 38 and 37 at the top for the maxes.
So let's do one at a time. Your match one? Is that, so did you get something?
37.
And then what was your change here?
11 points.
So you had a huge difference here.
Yeah.
11.6.
7.
11.7. What do we do with that number?
Average.
All of a sudden we've got Lauren's group. They have a piece of data that's radically different from the rest of the group. What do we do with that piece of data?
Well, we did match as well, and we had 1.8.
For a difference?
Yeah.
Let's look at this. All of a sudden we're getting some differences here. So the change in temper for the match, we had 11.7, 2.4, what did you have?
1.8.
1.8. What do we do with that? Do we average? Do we ignore? Do another test? Do we list them all? I mean, this is a serious problem. Like today, we've got some outlying data we've got to deal with, especially with greenhouse climate data. Data's argued. These topics are debated. So they've got to see that mistakes happen, errors happen, there's outlying data, and that's a real part of science. Every single one of the hands-on labs that we do, we talk about 2 pieces of content. The explicit content about what we're going to learn about that science piece of information, global warming or biodiversity, whatever we're learning, but also the nature of science. How does science actually work? Science is not clean, direct, linear, objective, recipe-like. It's messy, it's subjective. It takes a group of people wrestling with data to come up with a piece of knowledge. One of the things that we're going to see when we look at climate change data is people argue about the data. They say that this data is not important. This data was collected wrong. This data needs to be revised. Climate change data is debated, whether we agree with that process or not, but people debate that data and people argue about climate change. You have the same problem. This is not unexpected. Everybody was doing something a little bit different. It might have been your angle of your light or your angle of your tube. We have variables here that are going to be different, but we need to resolve this. We're not just going to nod politely at this and pretend it's going to go away. So for our class, what do you guys want to do about a change in data that doesn't fit what we think it should do? What do you guys want to do? So we're going to retest. But what are we going to do with these numbers? Are we going to include them or are we going to get rid of them?
Include them.
Include them.
And make an average.
I would say average.
What if we were to get, what if we tested 5 or 6 more times and Lauren's data, we're going to call it Lauren's data because just you reported it, Lauren's data is still really way off. Let's say we collect it 30 times and we have 30 times like this and then Lauren's way over here. Lauren, since it's your data, what do you think?
I think we should retest in the same kind of area that.
Okay, so retest very specifically in your conditions, okay? So
maybe like consider hers an outlier.
Consider hers an outlier and realize that it might change.
Yeah.
One of the things that we have to remember about all scientific knowledge is that it's tentative yet durable. Tentative yet durable. we're going to be taking climate data for the next couple of weeks, and everything is going to change. We're going to be slowly adding more and more data. So someone tell me, what does it mean when I say that scientific knowledge is tentative yet durable? What does that mean in terms of scientific knowledge? Has discovered the structure of the atom. Well, it wasn't laying out there somewhere and someone found it under a rock. Someone took some observations and created an explanation. All scientific knowledge is a human creation. Therefore, that's how it can be changed. That's how it can be tentative. If scientific information was discovered at some canon list that never changes, then science would stop. But because it's a human creation, it can change and it can grow and it can get better. Mr. Hansberry.
Tentative as in it's always changing.
Okay, it's always changing.
But durable is always going to be basic. You know, you have to have that kind of knowledge to change. It's always going to be acceptable.
Okay, so we've got to understand that science changes, but it doesn't change willy-nilly at the drop of a hat. Just because one person gets something different, we don't change all of scientific notation. That's really important for us to understand that science changes. Is there anything in science that does not change?
Law. Theory? Or laws.
What are laws based on?
Theory. Facts.
In science we call facts data or empirical evidence. Could we gather more evidence?
Mm-hmm. Yeah.
Could that theory or law then change?
Yeah.
Yes. There is absolutely nothing in science that is not open to change. Between observations and inferences. One of the things that a typical misconception or problem we have with students, especially at lower grades, is jumping to inferences before they've collected data. Inferences are great. You have to have inferences in science. You wouldn't get anywhere if you didn't have inferences. But back it up with empirical data first. Don't bring me hunches that are based on just ideas. I want hunches based on empirical facts and data. So we really, anytime we talk about conclusions, anytime we talk about new knowledge that we've generated, they have to show me where in the data they got those conclusions from.
Gravity.
Our ideas about gravity might change. The observations may stay the same, but the ideas about it may change. This lesson is twofold. Every time I do the lesson on climate change and greenhouse, whether I'm teaching it to elementary school, middle school, high school, or college, every time I do this, I want two outcomes. One outcome I told you up front. We need to look at how the different gases influence change. And when we finish collecting data, we'll look at all and we're going to see, how does water vapor change it? How does carbon dioxide change it? How does human exhalation change it? How does a match change it? After we collect lots of data, we'll make some big conclusions. So that's one thing that I wanted you to learn from this lesson. And that's the one I was up front with you about. But another thing that I want you to understand is about the nature of science. Science always changes. But it doesn't change just because one piece of data doesn't fit. It has to be durable. It has to be usable. If science just changed any old time, it would be like a moving target that you could never grab. You've got to be able to grab it and use it for a while. Another thing about the nature of science is whether or not it's influenced by our culture and by our prior knowledge. Is your work today influenced by anything culturally? About your culture or your prior knowledge?
Yeah.
How so?
The air conditioning.
Okay, absolutely. So the air conditioning, that's more of an external variable. But what about your prior knowledge? Do scientists have to think about their culture and their prior knowledge and their beliefs and their religion and their politics? Mm-hmm. Or should science be above all that?
It should be non-biased.
Yeah.
Is
science objective or subjective?
Objective. It's supposed to be objective.
Yeah, objective.
But the sheer nature, human nature, prevents that from being possible.
How so? Think about climate change. What are things that affect how we think about climate change?
Politics.
Religion, politics, and economics. And religion absolutely affects people's views of science. But in this sphere particularly, when we look at climate change, we're going to look at how politics and economics can influence how people read data. How many of you, before we started this lab, knew that carbon dioxide can influence climate change? Raise your hand. Did that influence what you did in the lab today?
I don't know.
Did it influence how you interpret the data?
Yes.
Yeah. Do you kind of already know what to look for?
Yeah.
Think about that. You already theoretically know what to look for. You kind of already know the answer. So every time we do new experiments on climate change or on global warming, we already have this idea or theory out there about it. So it does kind of influence to a little bit what we look for and what kind of patterns we make in the data. The next time we come into class and we finish our data collection, we get a lot more numbers. We'll start putting together a trend and a pattern in terms of the answer to which one of those gases is more powerful in climate change. Here's what I want us to do between now and then. Take a look at these questions. We're going to answer 1 through 3 kind of collectively as a group. I want you to look at 4, 5, and 6 here. They need to kind of get some ideas out of their head and say them out loud and listen to each other. That conversation is important, but it's still collective. The writing is where I'm going to hear individual answers. And then after the writing comes the model making. We typically do some type of visual model for every single lab, whether it's a Venn diagram or whether it's a drawing or whether it's a 3D model. I like to see visual models, and then we talk about the importance of models, the limitations of models, what a model can do for us, what inherently a model cannot do. All models have their limitations. So greenhouse gases are a great one. They'll all do some type of drawing with arrows from the sun bouncing back. They're all going to do some version of that. But what they include and what they don't include in the model will tell me what they think is important and what's not important. And a lot of times that will come out in a visual way that I won't get in writing because they're trying to be too perfect in their writing. They're trying to copy definitions and be exact. But in a model, because it has to be edited, I really get to see what they think is important, what is not important. I'll put these on Schoology. You don't have to write these down right now, so they'll be on Schoology. Think about the data we collected today. Why would a planet without atmosphere be cooler? Explain why we see regular fluctuations of CO2 levels in Florida in the winter and the summer. Explain how greenhouse effect works in general, and I want you to find the main anthropogenic sources of CO2. I'll put these on Schoology. Have those answered by the next time we come in so that when we do go to find patterns in the data, we can do it rather quickly. Do not lose your data. We're only halfway through. We've gotten into a habit in this class that a lot of the stuff, we use Schoology, which is kind of like a Facebook for schools. All of that stuff that I write on that whiteboard gets saved to a PDF file that they go to look at. We do not spend our class and time taking notes. I don't take notes in my class. They've got all that stuff written down for them. There's no need for them to write it down in addition to me writing it down. Now, every once in a while we'll write some stuff down, but my teaching style is very conversational, very oral, so we spend a lot of time talking, not a lot of time writing. Those whiteboards can be saved in PDF formats and they can go grab them when they need them.